we're going to take a look at rational functions. Let's start with the definition. The ratio of two polynomials is called a rational function, where both p of x and q of x are polynomials. So in the middle of that definition, we had an equation, f of x equals. We have a polynomial p of x in the numerator and a polynomial q of x in the denominator. Now we can look at various types of rational functions, but in this course we are only going to consider rational functions where p of x and q of x are relatively prime, meaning they do not have any common factors. Taking a look at example 1, we have 8 examples of rational functions. Most of them take the form that you would expect. Note that A and B, they have a simple polynomial, a linear in this case, on part A over quadratic. And on part B, we have a linear polynomial over a linear polynomial. Part C is not what we would typically consider a polynomial, but if we put the fourth degree polynomial in the numerator and then put it over 1, that basic polynomial function can now fit the definition of a rational function. Taking a look at E, you notice it has quite a few decimals and square roots and fractions in it, but that's okay because the powers in the numerator are integer powers and the powers in the denominator are integer powers. So it fits, both of these functions fit our definition of a polynomial, and since they're in a fraction together, they are now considered together a rational function. One last one that you would not normally consider a rational function is part H, but technically it does fit our definition. To evaluate rational functions, we're going to do what we normally do, just plug the numbers in and see what comes out. So on example 2, we're given two rational functions, f of x and g of x, and we're asked to evaluate 4 different x values. So for part A, f of negative 2, we're looking at this rational function. We have negative 2 quantity squared minus 1 over negative 2 quantity squared plus 8, which becomes 4 minus 1 over 4 plus 8, which is 3 over 12, and that reduces to a fourth. On part B, we're putting in the decimal value of 1.2 into f of x. So we have 1.2 squared minus 1 over 1.2 squared plus 8. And we will probably use our calculator to evaluate that. So let's do that over here. Hit alpha y equals, choose number 1, and enter in 1.2 quantity squared minus 1 in the numerator and 1.2 quantity squared plus 8 in the denominator. We hit enter. A calculator gives us this decimal, and that works just fine. And then on part C, we now move to g of x, which is a linear polynomial over a linear polynomial to make that rational function. And we're going to plug in the fractional value of a negative 3/2. So we have this at the beginning of our evaluation. Once again, if you want to use your calculator, you're certainly welcome to. Starting off, we have 2 minus 3 times a negative 3/2 becomes a positive 9/2. 2 times a negative 3/2 becomes a negative 3, and then plus 5. And putting all of that together, we end up with 13 over 4 as our function value. G of x, where x equals 3, is 2 minus 3 times 3 over 2 times 3 plus 5, which works out to 2 minus 9 in the numerator and 6 plus 5 in the denominator, which is a negative 7/11. Let's now take a look at the domain of a rational function, which, if you remember, the domain is the allowable x values. And for a rational function, it all comes down to the denominator. As you know, in fractions, the denominator cannot equal 0. So the domain of a rational function happens to be all of the x values where the denominator does not equal 0. Because if it equals 0, then we get something that does not exist, and that moves us into another topic of discussion for this section. That is coming up. So starting off, we are to find the domain of each of the following rational functions. So it's all about the denominator. We're going to say, okay, where 2x plus 3 equals 0, the function does not exist. So the domain is everything except where 2x plus 3 equals 0. So that's what that line there means. It means we're going to get all the values except where it equals 0. And so we have 2x equals a negative 3. And then divide by a 2. So the domain is all of the x values except negative 3 halves. So the domain of this function is equal to x such that x does not equal a negative 3 halves. We could also write this in interval notation. We could say that if we look at this as a number line, 0 here, negative 1, negative 2, negative 3 halves is right in the middle. We would say x is everything except that point. So we'd put an open circle above the negative 3 halves, and we'd say the domain of f is equal from negative infinity to a negative 3 halves. And then we skip over that negative 3 halves and pick up on the other side of it. And in interval notation, that would be our domain. Taking a look at part B, we have one that's a little bit more involved. Once again, the numerator does not matter at this point. To find the domain, we're going to look at the denominator. So taking the denominator and saying the domain is everywhere except where it equals 0, we can separate these two into two different equations, and we will get x cannot equal 2 and x cannot equal a negative 7/3. So if we wrote it in set notation, we would say the domain of G is all of the x values such that x does not equal a negative 7/3 and x does not equal 2. If we put that on a number line, negative 7/3 and 2 with a 0 somewhere in between them, we would say x cannot equal these values, but it can equal all the other values on that number line. So we'd end up with 3 intervals. So the domain in interval notation of G is going to be from negative infinity to a negative 7/3, and then a negative 7/3 to 2, and then 2 to infinity. The last one on this page, C, gives us h of x, which has a quadratic in the numerator and a quadratic in the denominator. So the denominator cannot equal 0. And you can find where that function cannot equal 0 a variety of ways. You can factor it, whereas x minus 3 times x plus 1 cannot equal 0. You could do the quadratic formula, which, if you remember, I'm going to say it cannot equal to. The quadratic formula is a negative b plus or minus the square root of b squared minus 4ac over 2a. So for this particular function, a would equal 1, b equals negative 2, c equals negative 3. I'm taking these coefficients here. So x cannot equal the opposite of b, which is a positive 2, plus or minus the square root of a negative 2 squared, minus 4 times 1 times negative 3, over 2 times 1. And then if you wanted to, you could also graph this function and see where the function has problems with its graph. So we could enter it in our calculator, and I would enter alpha y equals to get my fraction, and I would type in the numerator and then cursor down and enter in the denominator, x squared minus 2 times x minus 3, and then I would hit graph. And in this graph, I can see there's an issue happening here and an issue happening there. And the only way I could find exactly what those values would be, would hope that they were integers. And then I could go to second table. And if it shows me an error, then I know that my function is not graph, excuse me. My table is not set up correctly, so let me go into second table set and set my table start at 0 and put everything as auto and see if I can get my values. Right here at 3, you see there's an error, so I know that x equals 3 is a place that it does not exist. Then x equals -1, I have an error, so that's a place that my function does not exist. So I would say those two are exclusions on my domain. Now, if I follow any of these out, let me just follow this one, the first one where I factored. You could see how it works out analytically. And you get x cannot equal 3, and x cannot equal, that's a positive one, x cannot equal -1. So to write the domain of H, if we write it in set notation, we'd say x such that x cannot equal -1 and 3. If we view it as a number line, -1 here and 3 over there, x cannot equal these two places. So once again, we have 3 intervals. And we'd say our domain of H is going to be from -∞ to -1, -1 to 3, and then 3 to infinity.